This is the second part of our lecture about earthquakes. We will be talking today about the seismic waves and their types. We have two major types of seismic waves called body waves and surface waves. So body waves, from their name, they move throughout the entire body of the earth, not on the surface. And surface waves, in contrary, they travel only on the surface, not inside the body. Very simple comparison between the two types. For body waves, we have also two types of body waves called P waves and S waves. And for P waves, they are the fastest waves. We call them primary. They arrive first, and sometimes we call them compressional waves or longitudinal waves, and we will know why we call them these different names. And the particles of the body or the earth here, they move along the direction of the wave propagation. So if you have the wave moving from, for example, east to west, you will see also the particles of the earth moving in the same direction. So that's why it is the fastest. As you can see from the animation on the right side, look at this black square. See, you have compressions and dilatations, and the particles are moving in the direction of the propagation itself. And one important character of a P wave that they move through all media, solid, liquid, or gases here. So this is also a explanation for the seismic wave, and you can see there are pushes. And when it comes now to the S wave, we call it S because it's a secondary wave, so they come second. They come after, or they arrive after P wave. And their direction, or the particle movement direction, is different here. You will see they are shear waves, they arrive after P wave, and they propagate only in solid. So this is a major second difference between S wave and P wave. And they don't really cause a significant damage. Same thing as P wave also. Here an explanation. Here is an explanation. S shear wave, and this is explanation for the difference between S wave and P wave. Now the second major type of seismic waves is the surface waves. So the surface waves, as we said, that they are traveling always on the surface of the earth. They are slowest. They are slower than body waves, and they cause the most damage. And you can understand that easily because they travel on the surface, and we are living on the surface of the earth. So surface wave can be divided also into two types. First type is called love wave, and this name actually, love, comes after the name of the Professor Love, who discovered S wave. And you can see also here they are similar in their movement like S wave, but not in vertical. So it moves the ground from side to side in horizontal plane, but at right angles to the direction of propagation. So they cause damage to the foundation of structures. Second type of surface wave is called Rayleigh waves, also after the discoverer of this type of waves, and they move like rolling ocean waves. in elliptical shape. They roll along the ground just like a wave rolls across the lake, from up and down, or from down to up. And their amplitude is really high at the surface, and they decrease downward. They move ground up and down and side to side in the same direction that waving is moving. You can see here again, look at this square, the black one, and those blue circles, which they show the elliptical movement of the particles of the earth. Most of the shaking felt from an earthquake is due to rally. So the rally is the most destructive type of wave. At this, you will see this is only measuring vertical movement here, but Earth is moving in different directions. So we have another instrument, also seismograph, with another component for the horizontal or for lateral movement. And you can see on the left bottom here the seismogram. As I mentioned before, this is a piece of paper that has those signals drawn on this paper. Okay, how we locate earthquake? To locate an earthquake, or to locate the epicenter of earthquake, we need at least three stations. Each of them will create a circle. The center of the circle is this, as the earthquake station, and the distance from the center to the perimeter of the circle is the distance between the focus or the epicenter of the earthquake and the station. So from the station to the earthquake is one circle. So if you have two circles, they will intersect in 2 points. But we need to exactly locate the location of the earthquake. We need at least 3 circles to meet in 1 point. As you see here, the epicenter at the intersection of those orange or yellow, red, and purple lines. Okay. When it comes to the classification according to the depths of earthquakes, you'll see 3 locations. You have shallow earthquakes, less than 70 kilometers, for example, those green spots, and you have also yellow ones around 300 kilometers, and you have deep earthquakes, the red ones, more than 300 kilometers in depth. Now we come to the measuring of the earthquake, and we measure the earthquake in 2 aspects. Either we measure the intensity of the earthquake, or we measure the magnitude of the earthquake. And the intensity only measures the amount of damage. So it is not really a good indication or good indicative of the magnitude. So for the intensity, it's a measure of earthquake shaking and the amount of damage. But for the magnitude, we estimate the amount of energy. And you know what does it mean, amount of energy here? The amount of seismic waves released by the earthquake. So we usually depend on the magnitude more than intensity, because intensity, if the earthquake happens in the desert, for example, in the desert, you cannot just tell how much damage happens, because there is nobody living there. So intensity scale, it came after the scientist called Mercalli. That's why this scale, we call it modified Mercalli intensity scale, and was developed using California building and its standard as a standard for the default the fault or the drawback, and the thing is not right about this kind of scale, we call it drawback, is the destruction may not be true measure of earthquake actual severity. But for the magnitude scale, which we call it Richter magnitude, this concept introduced by Charles Richter in 1935, and it's based on the amplitude of the largest seismic wave recorded. And it is a logarithmic scale. So each unit of Richter magnitude equals 10 times increase in wave amplitude for the next degree, and 32 increase in energy for the next scale. Like the difference between 4 and 5, for example, you have 10 times increase in wave amplitude and 32 increase in energy between the two consecutive scales of Richter, like 4 to 5 or 5 to 6. So the nice thing about studying earthquakes that we have discovered the liquid area, or in the earth, by using something called S-wave shadow zone. And what does it mean, S-wave shadow zone? If you have stations or earthquake stations distributed along the surface of the earth, you will find some of those stations don't record S waves. And as we know that S waves don't travel in solid media, so it means that if you don't receive it, so it means that they pass through a liquid. So that's why you don't receive them. So cannot travel through liquids. The liquid outer core, you have a larger shadow zone, and you can see it starts from 103 degree to 103 degree for the other side of the earth. You see this bottom arrow, the curved arrow, show you where you don't record this S wave. Okay, we understand that for the S wave. How about P wave shadow zone? P wave shadow zone happens because you have refractions, you have different velocity density contrast inside the earth layers, or between crust and mantle. And as you can see here in the yellow area, all waves arriving without any disturbance. But once it comes to enter the liquid out core, which is the orange area, they refract. They have higher speed. So they refract inside this area, and when they go out of this part also they refract again, because it's going from high speed to low speed media. Then you have this area from 103 degree to 143 degree, you cannot receive P wave. So there's two difference between the S wave shadow zone and the P wave shadow zone. You can see the difference. So P waves through liquid, they travel through liquid and leaving low intensity shadow zone, 103 to 143 degrees away from the source, as you see from the figure. But P wave traveling straight through the center continue, and because the speed in the solid inner core are faster, they arrive sooner than expected if the core was all liquid. Good. This is enough for today, and inshallah in our next lecture we will learn about a new topic in our course of physical geology. Thank you and have a nice day. Bye.